Good afternoon, ladies and gentlemen, and welcome to my presentation, Reliability of Spur Gears, Determination of Stress-Dependent Weibull Shape Parameters for Tooth Root Fracture. This presentation has been held at the 31st European Safety and Reliability Conference 2021. My name is Axel Baumann, and my co-authors are Jochen Juskowiak and Bernd Bertsche. Here is an outline of my presentation. First, I will start with a problem statement and the starting situation for endurance tests in mechanical engineering. Next, I will show you our hardware-in-the-loop test rig, where we tested a Spur gear pair regarding its tooth root fracture lifetime. In the third chapter, I will show you the obtained test results. And in the fourth chapter, I will evaluate these test results with the help of Weibull distributions. In the fifth chapter, I will show you the application of stress-dependent Weibull parameters, especially of a stress-dependent shape parameter B. I will close my presentation with a summary and an outlook. Okay, what is the starting situation for endurance testing in mechanical engineering? It is well known that there is a stress dependency of the Weibull shape parameter in mechanical engineering. First, the application of a Weibull distribution for different failure modes is very common in mechanical engineering. Here you can see a 2 and a 3-parametric Weibull distribution. When we speak of a 2-parametric Weibull distribution, we have the shape parameter B and the characteristic lifetime T. With the help of different shape parameters, we are able to describe different failure modes within mechanical components. By adding a failure-free time T0, we come to a 3-parametric Weibull distribution, which is commonly used with fatigue failures. With the help of the Weibull distribution, we are able to describe different failure modes like early, random, and fatigue failures. Next, there is an interaction between the occurring stress and the bearable stress, which defines the failure behavior of each machine component. The occurring stress is depending on the load and the shape of the mechanical part. The bearable stress is mainly defined by the used material and the machining of the part. Altogether, we have a special or certain reliability, which is defined or described by the shape and the position parameter of the Weibull distribution. In literature, you can state that the failure behavior of many different mechanical components is well known. The claim is usually when we have higher load, we have also larger shape parameters of the Weibull distribution. But for instance, in the case of bearings, the literature is inconsistent. Simplified, here is a constant shape parameter used, but it's also known that there is negative correlation between load and shape parameters, for instance, in electrical isolators. Here you can see some commonly used mechanical components like shafts. Here we can see a shape parameter in between 1.2 and 1.8 for fracture failure mode. For bearings in the failure mode pitting, we see for ball bearings a shape parameter B of 1.1, and for roller bearings in the range of 1.3. And for gears, we have for pittings a shape parameter in the range of 1.1 to 1.5. And for fracture, we see a quite large spread in the shape parameter from 1.1 to 2.2. Additionally, it's important to know that testing on test rigs is usually more demanding than in the field with the customer. And we have various sources for reliability information which are independent from each other. Some companies of mechanical components use attempts of predecessors to define the reliability of the future product, but we also have different samples in testing, and there are various databases in literature known which makes it difficult to use the right shape parameter for lifetime testing. With the help of our investigation, you are able to apply a shape parameter which is stress dependent, and the lifetime prediction of your gearbox is optimized. Here you can see the used hardware in the loop test rig and the tested Spur gear pair. First of all, we have on the input side a drive motor which is connected to the test transmission via a torsionally stiff coupling. The transmission output shaft is connected to the brake motor, which applies the load to the gear. In the photo, you can see here in the middle the single-stage transmission, which consists of a single-stage Spur gear pair. The transmission input side is connected to the drive motor and the output shaft is connected to the brake motor. On the transmission input side, we have an incremental encoder to evaluate the speed of the input shaft. The whole setup is placed on a machine frame which is isolated via air suspension elements to the environment. The electric converters here in the background are used for control of the drive and the brake motor. In this picture you can see the tested Spur gear pair. It's a helical gear which is commonly used in vehicle transmissions. The material is a 20 mangan chrome 5, which is also a commonly used material in automotive gearbox design. The fatigue strength torque of this gear pair is calculated with 450 Newton meters. In our investigations, we applied a speed on the drive spur gear, which is located on the transmission input shaft. On the transmission output shaft, we have the driven spur gear, which is additionally shot peened to control the fracture on the drive spur gear. On the downside of this slide, you can see a photograph of the fracture surface. The surface can be divided into two parts. First, we have the fatigue failure part of the crack, and in the middle you can see the so-called forced failure of the crack surface. In this picture you can see that there are two fracture positions, which claims that the load on each gear tooth is equally the same in each test. Now I will come to the test results which we obtained in the lifetime testing. First of all, we defined three different load levels above fatigue strength torque of 450 Newton meters, which are 470, 500 and 530 Newton meters. On each load level, we tested 10 specimens for a high confidence level of the life cycle data. Additionally, we added a torsional vibration to simulate the behavior of an internal combustion engine, which speed is not constant, it is vibrating in between a certain range of an amplitude. In this case, we used plus minus 10%, plus minus 20%, and plus minus 30% on top of the constant load. When you see here the life cycle data, first of all, when we rise the load, the life data overall is decreasing, which is obvious. When we additionally apply a torsional vibration to the load, the life cycle data further is reduced due to the higher load. When we evaluate the test data with Weibull distribution, you can see what's happening here. First of all, we evaluated the test data with a constant load in this case. So on the x-axis we have the lifetime t, and on the y-axis we have the failure probability ft. We've chosen a three-parametric Weibull distribution since the fatigue failure is a matter of failure-free time and it's commonly used that we have chosen a three-parametric Weibull distribution. The regression analysis is used for calculating the Weibull slope, and a 90% confidence bound is applied to the data. When we evaluate the parameters of each Weibull distribution, we come to following conclusion. The shape parameter B in median is decreasing with rising load, which is quite interesting. The failure-free time is, when we rise the load, also decreasing. The correlation factor K, its value is almost close to 1, which means the calculated Weibull distribution is a good fitment to the obtained test data. Next, we evaluate the load stage plus minus 10% torsional vibration. What you can see, the failure-free time is further reduced, and the regression analysis and the 90% confidence bound is used as before. When we now look on the shape parameter B in median, we see that the value of the B is constant for each load level around 0.9. Again, the failure-free time is further reduced with rising load, and the correlation factor is in this case also close to 1, which means a good fitment of the Weibull distribution to the obtained test data. Next, we see here the load level plus minus 20%. The failure-free time is further decreasing, and in this case the shape parameter B in median is around 1.1 with one exemption, 0.9, but we can state it is almost constant in this load case. With the highest torsional vibration plus minus 30%, we have a further reduction of the failure-free time. And in this case, the shape parameter B of the Weibull distribution is rising with rising load in the torsional vibration area of 30%, from 0.9 to 1.6. To evaluate and come to a conclusion via application of a stress-dependent Weibull parameter, we have chosen this graphic. What you can see here is the characteristic lifetime t minus t0 on the x-axis and the shape parameter b on the y-axis. For each load level, we added a circle which is representing the 95 confidence bound of the shape parameter b, which means when we have a small radius, there is a small spread in the shape parameter b, and when we have a large radius, the confidence bound is quite high. What you can see here, when we have no load, vibration load plus minus 0%, the load levels are on indistinct areas of the shape parameter B, which is here around 0.5, 0.6 up to 1.0 and 1.3. When we add torsional vibration to the load, the shape parameter is concentrating here in the range of 1.2 down to 0.8, and the spread is quite high of the shape parameter B. One exemption in this case is the highest load level, 530 Newton meters and 30% torsional vibration. In this case, we have the highest shape parameter B with the highest 95 confidence bounds. Another display of the behavior of the shape parameter can be seen here. On the x-axis, we have the load level with increasing vibration excitation and the corresponding shape parameter B. In the middle, there is the median of the shape parameter B and within its 90% confidence bounds. In the case of 0% torsional vibration, the shape parameter B is decreasing with rising load. When we come into the range of 10 and 20% vibration, the shape parameter B is almost constant with a value in between 0.9 and 1.2. And when we look at the torsional vibration plus minus 30%, we have a sharp rise of the shape parameter up to 1.6 within its 90% confidence bounds. Okay, to sum up, you've seen the shape parameter of the test data on different load levels are clearly stress dependent. And the behavior of the shape parameter can be described as follows. First, the shape parameter decreases with increasing load in high cycle fatigue area without vibration excitation. And the shape parameter B remains constant or increases with increasing load in the low cycle fatigue area with vibration excitation. The consideration of a stress-dependent shape parameter leads to a more reliable prediction of the gearbox lifetime. If you found this useful and need consulting or advice in the field of gears and reliability, I'm happy to hear from you, and I will talk to you later.